This presentation introduces a way how to realize FPGA-based massive regression tests with minimal effort and time. When implementing FPGA-based with Testbench, we had spent a lot of time for developing test programs and for debugging hardware design and test programs. The key point of this talk is to minimize such overheads by implementing a fully synthesizable test bench, adopting a customized process core called test instruction set core, shortly TISC, and implementing synthesizable memory model without using actual physical memory device. The content of this talk is rather focused on the multimedia IP verification, so it is worth to summarize recent challenges of this domain. In application processors for mobile devices, multimedia IPs such as camera IP, video, display, and audio processors, and now including AI processors such as NPU and DSP, have been the essential components. As its importance grows, spec and design changes just before RTL freeze are inevitable and natural, which makes a load time for DV extremely short. One common challenge of multimedia IP verification is that they have so many configuration registers for trading off image qualities, performance, and power. Many configuration register means very wide random space which cannot be covered by simulation in allowed short DV time. So, in multimedia IP verification, FPGA or emulation-based massive regression tests are mandatory. Developing and maintaining FPGA regression tests separately from simulation-based DV test bench require considerable cost. It is not free. We had to use two test bench architectures for FPGAs. One is simple and another is complex. In the simple test bench architecture shown in the left side of the slide, test programs running on the host machine access to configuration registers of DUT directly through USB or PCI links. Although it is simple, there are several limitations. Register access by test program is very slow and its cycle-level behavior is unpredictable. Extra memory introduces uncertain bus latencies which limit reproducibility of found issues. Once an unreproducible issue happens, considerable time is required to narrow down the symptoms with painful experiments on FPGA. Alternative complex test bench architecture can resolve these problems by embedding a microcontroller and hiding DRAM latencies by implementing a clock gating scheme in the synthesizable test bench. However, it incurs the other difficulties and costs. Now, developing and debugging test programs require expertise on the embedded software development, which most DB engineers are not familiar with. Although clock gating scheme can improve reproducibility of tests, it slows down the effective duty clocks significantly, which increases total regression turnaround time. Finally, the author would like to note that downloading or uploading data streams to or from SRAM takes considerable time for both architectures. This is very critical for regression turnaround time. In this slide, requirements of new solutions are listed up. Among them, fully controllable bus access latency without clock gating scheme are considered first because they are the most critical factor of regression turnaround time and debugging cost. The idea is simple. Eliminate the problems stems from SRAMs by eliminating SRAM itself from test bench. Synthetic memory version IP is the implementation of this idea. However, eliminating SRAMs from FPGA test bench means that test programs and data should reside in the internal SRAMs of FPGA. Since multimedia IPs have plenty of configuration registers, the size of test programs often exceeds the capacity of block SRAMs of FPGA. To mitigate this problem, a new processor core with special instruction set, which is capable to implement test programs in very small memory footprints, was invented. Based on this idea, the author had found that the other remaining requirements could be surely covered by implementing employing simple augmentation of the two ideas. This slide shows the microarchitecture of test instruction set core, shortly called as TISC. The program memory is restricted as only 64 kilobytes, which is very small. No external memory interface and no cache controller for external program loading. Address generation logic is simple because all of address values, including program counters, are only 16 bits. To make 64 kilobyte SRAM size feasible, variable length instruction set format is adopted. A configured register access could be encoded into various instruction formats of different byte lengths, considering their addresses, write data, and relationship with the previous instructions. Special instructions, such as repeated APB accesses with automatically increasing addresses, is very effective for reducing test program size. TISC embeds a hardware accelerator called RNGNet for generating a series of numbers of specific constraints, such as lookup tables. By using RNGNet, thousands of random numbers and their write accesses could be replaced with a single instruction. The checksum calculators embedded in the TISC always observes APB read accesses and calculate checksums of them so that the resulting checksum values could be used for checking register mapped outputs of duties. This is also very effective for reducing both program size and test time. To make test program implementation simple, TISC internally contains essential peripheral functionalities such as interrupt controller, timers, and so on. All of these functionalities are mapped to dedicated registers. TISC provides two APB masters, one for duty and another for variation IPs. Delays between consecutive APB accesses could be controlled by setting dedicated special registers. Programmable inputs and outputs are mapped to specific registers so that they could be accessible directly by test programs. The programmable I/O units provide 64 bits inputs and 64 bits outputs, which could be connected to output and input ports of duties directly. The programmable I/O units also provide dedicated handshaking channels that implement valid ready handshake behaviors. With a mixture of 64 bits inputs, 64 bits output, 3 master handshaking, and 2 slave handshaking, various complex duty interfaces such as FIFO put, FIFO get, XA master, and X slave could be implemented and serviced. The other peripherals such as timer, checksum calculators, and RNGNet have their own dedicated registers so that their behaviors could be controlled by test program very easily. The main user of TISC is DV engineers who are not familiar with debugging software running on an embedded processor. For easier debugging by DV engineers, minimizing branch instruction calls in a test program is helpful. For this purpose, TISC provides per-instruction-wise conditional execution. For each of instruction, a condition to execute that instruction could be specified. The basic concept of per-instruction-wise conditional execution is very similar to ARM instruction set, which allows only 4 flags, 0, overflow, carry, negative, for specifying per-instruction conditions. The difference of TISC is that it allows a rich set of conditions, including 16 general-purpose flags, which can be set by arithmetic operations and move instructions, 32-bit general-purpose registers, and 64-bit input and handshaking events detected by programmable I/O unit and peripheral devices such as timers. Many DV owners prefer to using conditional executions than branches because it is more suitable and easy for waveform-based analysis. Multimedia IPs often contain a set of configuration registers that share the same constraints and the same dependencies. Lookup tables are such registers. For an example, Bayer image processor contains LUTs for bad pixel correction whose entry size is 4000, and LD 16 kilobyte is required to hold whole values. If a design contains multiple LUTs, the program memory will exceed our limitation 64 kilobyte. It is possible to write the function that generates random LUT values at runtime. This is a general way and still possible in TISC. As a better solution, TISC provides random number generation network, shortly called as RNGNet for more simplicity. RNGNet is a generalized network mainly targeted for LUT generation. The author had investigated all of random LUT generation functions currently used in multimedia IP test benches and devised a generalized architecture that can cover the majority of them with acceptable hardware area. RNGNet can be divided into 4 parts. At the center of it, total 8 pseudo-random number generation modules of 8 bits wide exist, which are backupped with limiting functions. Then, 8 random numbers could be selected, combined, and added to form a more complex 13 2 bits wide random numbers. And then, either offset or previous values are added to model DC components or dependencies, respectively. The time for updating the center random number generators could be randomly generated by another 3 bits wide programmable random number generators as a green colored box in the figure. This is very useful to model pseudo-random number sequences of different update frequencies. This slide shows an example configuration of RNGNet to generate monotonically increasing LUT values. This graph is what you can get with a simple pseudo-random number generator that generates delta values between adjacent 2 steps. These 2 graphs are what you can get with RNGNet, which is an addition of 2 independent sequences. One is frequent small stepping and another is occasional large stepping. By activating more sequences of different frequencies and steppings, we can get more complex LUT functions. The output of RNGNet is mapped to a dedicated register. By using repeated APE write instructions that refers to the register, then it is possible to replace thousands of write operations with just single instruction. Now let's move to the next topic, inserting memory version IP. This is a synthesizable XI slave interface model which behaves as like memory without real physical memory devices. For read data synthesizer generate pseudo-random values at runtime. For write data, checksums per byte length are calculated instead of holding whole contents for output checking. Random delay insertions for address and response channels are another key function of this version IP for higher version quality. This slide shows the microarchitecture to synthesize read data. The core function is the address-to-data spreader, which is an XOR-based hash function that takes address values as the key. The author had adopted XOR-based hash function because it is deterministic and independent from the access order and easy to implement with a very small area overhead. The values generated by address-to-data spreader could be processed by several operation layers, including logical operation, 3x3 filtering, addition operation, and clipping, to be more suitable for verification conditions. Note that downloading input data is no more required. For write data, checksums of written values are calculated instead of keeping all of them in a real memory device. The author considered 2 important requirements of checksum algorithm. One is the order independence of written data, and another is detection capability of bugs that rise to different address locations. To meet these requirements, checksums are calculated for each byte lane, accumulating write values. Before accumulation, write values are XORed and rotated with their associated addresses so that the address data pair are reflected in the resulted checksum. This checksum is well applicable for the IPs with multiple XI masters. We can get total checksums simply by adding checksums of individual XI masters. Note that uploading written data for output checking is no more required as like write data. In fact, there are many other technically proven and more sophisticated solutions for developing synthesizable test benches. Some DB engineers do not fear of employing embedded processors in their test bench. A few DB engineers are familiar with HAF technology, which is the more general and flexible way. However, most of or majority of DB engineers want to stay their technical safe zone, which are simulation-based constraint test bench development. This is the same for FPGA engineers who want to focus on FPGA synthesis and implementation issues instead of studying IP-specific domain knowledge. In the team management viewpoint, a methodology that can separate the roles between DB and FPGA was highly demanded. The proposed test bench architecture guarantees perfect reproducibility of test behaviors because it is a closed system while test is running. So there is no need to debug issues using FPGA systems directly because the issues always can be reproduced by simulation. For FPGA owners, sharing the test identification number with DB engineers is enough. So both DB and FPGA engineers can stay in their safe zone. In fact, writing test programs for the task is a big challenge. This challenge was mitigated by reusing and augmenting DB test benches. Based on the original DB test bench, generation codes for input images, LUTs, and configuration strategies are slightly modified to gather intermediate data. The collected intermediate data are fed into a simple script that generates TISC instruction codes. For DB engineers, this takes only several hours. The clear separation of DB and FPGA engineers allows us to apply FPGA-based regression tests in more IP verification projects without increasing human resources. In conventional FPGA test bench, no matter how it is simple or complex, FPGA engineers should implement their own FPGA test programs, consuming unacceptable time. So, we could apply FPGA-based regression tests to only 2 IPs. By taking the new testbench architecture, FPGA engineers does not spend their time in understanding IP specification, writing and debugging test programs. So, the FPGA engineers can concentrate on their original mission, which takes only 1 hour for integration and up to 12 hours for synthesis, which means that the first FPGA regression test of an IP is ready just in a day. So now we can apply FPGA-based regression tests to 10 more multimedia IPs and found many extreme corner cases which were not detectable by simulation. Now the team is totally free from debugging on FPGA system. In this presentation, the author has been presented a way for realizing FPGA-based regression tests that imposes negligible overheads. The area overhead is negligible because total area of TISC and synthetic memory VIP is less than 1% of conventional DUTs. The human resource overhead is negligible because no dedicated engineers were assigned to both FPGA and DV for FPGA-based regression test data. Only we require a person who should run the FPGA board with the test programs provided by DV engineers. This is easy job and any novice engineer could do that. Now, DV engineers can take advantage of FPGA-based regression tests without expanding their expertise into this area. With this new capability, some DV engineers are changing their verification concept from constraint random testing to full combinational testing, which is the most promising way for complete verification. One example is verification of image scalar, in which all of possible scaling ratio was fully touched. Thank you for listening.